The WKB Approximation 1. It can be a challenge to solve the Schrödinger equation for the bound state energy levels of an arbitrary potential well. An alternative approach that can yield good approximate results for the energy levels is the WKB approximation, named for the physicists Gregor Wenzel, Hendrik Kramers, and Leon Brillouin, who pioneered its application to quantum mechanics. The WKB approximation begins from three physical statements, the first one being, according to de Broglie, the magnitude of momentum p of a quantum mechanical particle is p is equal to h over lambda. And second, the magnitude of momentum is related to the kinetic energy k by the relationship k is equal to p squared over 2m. And finally, the third statement, if there are no non-conservative forces, then in Newtonian mechanics, the energy E for a particle is constant and equal at each point to the sum of the kinetic and potential energies at that point. E is equal to k plus u of x, where x is the coordinate. Part A. Combine these three relationships to show that the wavelength of the particle at a coordinate x can be written as this. Thus, we envision a quantum mechanical particle in a potential well u of x as being like a free particle but with a wavelength that depends on x. It's a function of position. Lambda is a function of position. So let's do this. So first of all, we are using the de Broglie relationship. The momentum of a quantum particle is equal to Planck's constant divided by the wavelength. Second statement, kinetic energy of this particle is equal to its linear momentum squared divided by 2m. Third statement, if there are no non-conservative forces, total energy is its kinetic energy plus its position-dependent potential energy, which is p squared over 2m plus its potential energy, u as a function of position, which can be written as, if I write with the common denominator, p squared plus 2m times the potential as a function of position divided by 2m is equal to the total energy of the particle. And here I can isolate p squared from this equation. So let's do that. P squared is equal to 2m times, 2m goes here, 2m times E minus 2m times U. So it is 2m times the energy E minus position-dependent potential. And that's equal to, according to the Broglie relationship, h squared divided by lambda squared. So we can calculate lambda here as lambda, which is position dependent. Lambda is a function of x. So I take the square root of both sides of this equation. Square root 2me minus u is equal to h over lambda. So lambda is h divided by Planck's constant h divided by 2m e minus u of x inside the square root. So in part A, we were asked to show this result. Basically, wavelength can be written in this form as a function of x. Part B, When the particle moves into a region of increasing potential energy, what happens to its wavelength? Now, if the total energy is greater than the potential energy, we have for total energy greater than the potential energy, we have unbound states. And as the potential energy, E of x, approaches the total energy, what happens to the denominator here? This is approaching 0, that means wavelength is increasing. So the denominator in the wavelength expression decreases. All right. So as the potential energy increases, the wavelength increases. That's our conclusion. Let's look at part C. At a point where the total energy is the potential energy, Newtonian mechanics says that the particle has zero kinetic energy and must be instantaneously at rest. Such a point is called a classical turning point, since this is where a Newtonian particle must stop its motion and reverse direction. As an example, an object oscillating in simple harmonic motion with amplitude a moves back and forth between the turning points x equals minus a and x equals plus a. Each of these is a classical turning point, since the potential energy 1/2 k prime x square equals the total energy 1/2 k prime a square. In the WKB approximation for lambda as a function of position, what is the wavelength at a classical turning point? That means the total energy is the potential energy when capital E is equal to capital U of x. What happens to the wavelength? You can see here I'm getting h divided by 0. So lambda of x is going to be h, and as u approaches e, this is becoming 0 plus, and what happens is the wavelength lambda of x is going to approach infinity. So we will get an infinite wavelength as we approach a classical turning point. Part D. For a particle in a box with length capital L, the walls of the box are classical turning points. Furthermore, the number of wavelengths that fit within the box must be a half integer, so that capital L is equal to n lambda over 2, and hence L over lambda is n over 2, where n is an integer 1, 2, 3, etc. The WKB scheme for finding the allowed bound state energy levels of an arbitrary potential well is an extension of these observations. It demands that for an allowed energy E, there must be a half integer number of wavelengths between the classical turning points for that energy. Since the wavelength in the WKB approximation is not a constant but depends on position x, the number of wavelengths between the classical turning points A and B for a given value of the energy is the integral of 1 over lambda as a function of x between those points is equal to n over 2. Using the expression for lambda as a function of position you found in part A, show that the WKB condition for an allowed bound state energy can be written as integral from a to b square root 2m e minus u of x dx is equal to nh over 2. Okay. Now, for the particle in a box states, remember we were supposed to have sign functions because the wave function has to disappear at the two endpoints, vanish, which means we have a node in standing waves. So capital L is equal to n lambda over 2. This is for particle in a box. And therefore, we reach the conclusion n over 2, integer number over 2, is equal to L over lambda. But this is for a constant wavelength. So in the WKB approximation, the wavelength is normally 1 over lambda is equal to n over 2. L is equal to n lambda over 2. But L is normally calculated as integral a to b dx. But here, if lambda is a constant, this is going to give us L, so L over lambda is n over 2. But if lambda is not a constant, it depends on the position, then we have to put lambda here inside this integral, and this must be equal to n over 2. This is for n equals 1, 2, 3, etc. This is WKB approximation. Okay, so that means if I go back to my result in part A of the problem, integral a to b dx over lambda, but lambda is h over square root 2m e minus u. So it is, for 1 over lambda, this is going to go upstairs, 2m e minus u of x inside the square root divided by Planck's constant dx must be equal to n over 2. So this tells us that integral from a to b 2m e minus u of x inside the square root dx must be equal to nh over 2. nh over 2, where n is an integer, 1, 2, 3, etc. And what are a and b? A and b are classical turning points, where the kinetic energy is 0. So this is the result of our WKB approximation. Part E. As a check on the expression in part D, apply it to a particle in a box with walls at x equals 0 and x equals L. Evaluate the integral and show that the allowed energy levels according to the WKB approximation are n square h square over 8ml square. Hint, since the walls of the box are infinitely high, the points x equals 0 and x equals L are classical turning points for energy E. Inside the box, the potential energy is 0. So for the infinite barrier square potential, we have the two turning points A equals to 0 and B equals to L. Our potential energy between 0 and L is equal to 0, and that means the integral from a to b, which is 0 to L, square root 2m e minus u, but u is 0, so it is square root 2m e dx, and square root 2m e doesn't depend on x, so it is L times square root 2me is what we get. This must be equal to nh over 2 using the WKB approximation. So that gives us the energy levels when I square both sides and square h square divided by, I will get a 4 here multiplied by 2, 8 m L squared, which is something we are familiar with for particle in a box states. Part F, for the finite square well shown in figure, show that the WKB approximation expression given in part D predicts the same bound state energies as for an infinite square well of the same width. Hint, assume the total energy is less than the potential energy, then the classical turning points are x equals 0 and x equals L. So this is talking about bound states. This shows that the WKB approximation does a poor job when the potential energy function changes discontinuously as for a finite potential well. So for this finite potential well, inside the well, the potential energy is 0. And x equals to 0 and L are the classical turning points. Why? Because the total energy is less than U0. So when we reach this point, that's our classical turning point for the bound states. And the solution that we will obtain here using the expression in part D will be identical to part E. Identical to part E. Because the finite barrier that we have, the finite barrier height, so at the turning points E is equal to U0. The finite barrier height U0 is not part of the calculation. So the WKB approximation works best for smoothly varying potential energy profiles. Here, because it gives us the wrong answer for this potential energy profile, taking these two endpoints as the classical turning points. Okay, so in this problem we have seen, we were introduced to the WKB approximation, which is based on three assumptions. Quantum mechanical particle momentum is h over lambda, kinetic energy is p squared over 2m, and total energy is k plus u, a constant in the absence of non-conservative forces. So using these equations, combining these equations, we have shown that the wavelength that depends on x is given by this expression, and for energies greater than the potential energy, this would have unbound states. For potential energy approaching the total energy, the denominator decreases and we will have lambda becoming finally infinity when E is equal to U at the classical turning point. At a classical turning point in a particle, for a particle in a box with infinite barriers, we have an integer times half wavelengths as the total length of the box, the distance between two barriers, because we have to have vanishing boundary conditions. And when lambda is a function of x, instead of this equation, we have n over 2 is integral between turning points dx over lambda, And if we substitute the expression we found in part A, we reach the WKB approximation. When we apply it to the particle in a box, where the potential energy is zero inside the box, we obtain the energy levels inside the box to be identical to the ones that we know. But if we apply it for a potential with a finite barrier height, and we take these two endpoints as the turning points, since this finite barrier height doesn't enter the calculation, we have to do inside the box, this is zero, this is identical equation for the finite barrier height particle in a box. Therefore, we get a different answer, the same answer as the infinite barrier problem, which suggests that this doesn't seem to work for this case. So the answer we reach identical to part E. Therefore, the WKB approximation doesn't work with this abruptly varying potentials, as you can see here, except for the obviously particle in a box states, but it works for smoothly varying potential energy profiles, and we will see examples of this in the upcoming videos.